We're all seeing these incredible videos of humanoid robots doing things that look like they're straight out of a movie. But the dream of having one of them in your house actually helping you out, that still feels really far away. Today, we're going to dig into the super interesting reason why. And yeah, this is the central puzzle, isn't it? It's where things get really weird. You see a robot from a company like Boston Dynamics doing parkour, dancing, things that are just mind-bogglingly athletic. It really seems like they can do anything. But then you ask a top expert if that same robot could, say, reliably walk up any random flight of stairs or open any door it comes across. And the answer you get is just blunt, not reliably. And that's coming from one of the smartest people in the entire industry. See, this isn't just some little bug they need to fix. This is a huge fundamental challenge. And it shows this massive gap between what looks good in a demo and what's actually useful in your home. So let's call this gap what it is: the robot paradox. How can these things be so incredibly capable and, at the same time, so clumsy? Let's break it down.
It's this wild contrast, right? I mean, these athletic feats are truly amazing, but the very same machine that can land a perfect backflip might just completely fail at something a 2-year-old can do, like turning a doorknob. So how did we get here? How did we build robots that are both superhuman and, well, kind of useless at the small stuff?
To really get it, we've got to rewind a little bit. We need to look at the 3 giant leaps in technology that made all those cool athletic feats possible in the first place. Okay, so the first big breakthrough was all about the software. It's something called deep reinforcement learning. Now, instead of engineers trying to hand code every single tiny movement, they just don't. They let an AI practice on its own inside a computer simulation. It's like a video game where the AI can fall down and get back up millions and millions of times until it finally figures out the best way to walk and balance. That's how we get that smooth, almost lifelike movement. Of course, all that fancy AI training is worthless if the robot just shatters the first time it falls over in the real world. That's where the second big shift came in, this time in the hardware. The old motors were super rigid and stiff, but these new ones, called proprioceptive actuators, are totally different. They're what's called compliant, which is just a fancy way of saying they're kind of springy. They can feel forces and absorb impacts, a lot like an animal's muscles. This tough new hardware was the key that let the AI actually work outside of the simulation. And the final piece of the puzzle tied it all together. This is where it gets really cool. Using a type of AI similar to what's in chatbots like ChatGPT, researchers gave robots a brand new way to understand us and the world. You can just say something simple like, "I'm thirsty." The robot can then see a bottle of water, understand your goal, and figure out the steps it needs to take to go get it for you. It's this incredible combination of sight, language, and action. So, you've got this amazing AI brain, this super tough and agile body, and a way to understand plain English. What else could you possibly need? Well, it turns out there's this one crucial thing that's still missing. Let's call it the physics gap. And as MIT researcher Pulkit Agrawal puts it, for robots to really work like us, they have to master physics. Now, we're not talking about quantum mechanics or anything. We're talking about the simple, everyday physics of force and touch, the kind of stuff you and I navigate every single second without ever having to think about it. Okay, this slide is really the key to the whole thing. See, most robots today run on something called position control. They are absolutely brilliant at moving their hand to a very specific point in space, an X, Y, Z coordinate. But that's not how we work. Humans run on force control. Think about when you grab a doorknob. You're not thinking, move my hand to these coordinates. No, you're feeling for the pressure, the resistance. That's the huge difference between knowing where to go and knowing how to interact once you get there. This brings us to a perfect way to picture the problem: the egg versus steel challenge. A robot using position control can be told the exact coordinates to pick up an egg, no problem. But without force control, without a sense of touch, it has no idea how hard to squeeze. It might use the same amount of force for a delicate egg as it would for a solid steel ball. And, well, you end up with an omelet on the floor. This inability to feel and manage force is the real reason they seem so clumsy. So the result of all this, when a robot actually has to touch and manipulate something in the real world, it has to compensate for its lack of feel by being incredibly, painstakingly careful. It moves super slowly, relying on just pure positional accuracy to try and not break things. And that's why you see a robot that can sprint like an Olympian suddenly move like it's stuck in molasses the second it tries to pick up a screwdriver. And make no mistake, this isn't some minor issue or a feature they'll just add later. As Scott Queendersma, who used to be at Boston Dynamics, says, making force a first-class citizen, meaning a core, primary part of how robots think, is absolutely required. It's not a nice-to-have, it's a must-have. Okay, so if the problem is all about teaching robots how to feel, how in the world do you do that? Well, right now, researchers are basically exploring 3 different paths to try and solve it. The funny thing is, nobody agrees on the best way forward. There are 3 competing ideas right now. The first camp says we just need more data, a lot more. A ChatGPT-style approach, but for physical actions. The second group argues that today's AI is just built wrong for this task, and we need to start over from scratch, building the laws of physics directly into the AI's foundation. And a third team is focused on using those simulations to teach robots to be more flexible and springy, reacting to the world instead of just moving to preset spots. The fact that the smartest people in the world can't agree on the right path tells us something really important about where we are right now. And that brings us to this final, really powerful idea to help us understand it all, the Volta stage. A roboticist named Russ Tedrake came up with this analogy. He compares where we are today to the very early days of studying electricity. Back then, scientists like Alessandro Volta discovered that if you took a dead frog's legs and zapped them with a bit of electricity, they would twitch. It was incredible, a demonstration of this powerful, mysterious force. But here's the thing, they had absolutely no idea why it worked. They were still decades away from understanding the fundamental rules of electromagnetism, what we now know as Maxwell's equations. And that is exactly where we are today with robotics. Those backflips, the dancing robots, the parkour, those are twitching frog legs. They're a stunning, undeniable sign that we've tapped into something powerful. But we haven't written our Maxwell's equations for robotics yet. We haven't figured out the fundamental science behind physical interaction and force control. So, the next time you see one of those viral robot videos, you'll have a totally new way to look at it. Be amazed by the athletics for sure, but then ask the real question, the one that gets to the heart of this whole physics gap. Don't just ask if it can run. Ask, can it feel the tiny twisting resistance of unscrewing a bottle cap? Because when it can finally do that, you'll know the future is really here.